Hello, I want to finish up this PowerPoint that we started last time and then take a look at what it's going to look like next time for the next PowerPoint. Remember, we left off talking about Descartes' rule to be able to identify how many positive and negative roots we might have. So here we get a sign change, so that's 1. Negative, no sign change. Second sign change, that's 2. Which means we could possibly have 2 positive roots. Remember, we always subtract by 2s, so it could also be possible that we have 0 positive roots. For the negative roots, imagine that we plug in negative x in for all the x's. Negative x cubed would be negative x cubed. Negative x squared actually turns positive, so it keeps its sign. Negative x cancel each other out, so that makes plus x. And then plus 3 stays plus 3. No sign change there. 1 sign change, no sign change there. So we could have 1 negative root. We can't have -1 negative roots, so our playout is either 2 and 1 or 0 and 1. Possible total number of zeros. Well, max degree is 3, so we could potentially have 3 zeros at the most. So odds are it's probably going to be 2 positives and 1 negative. It could also be no real solutions, and maybe like complex or imaginary, crazy like that, in which case you'd have 0 positive roots and then 1 negative root. Okay, in this problem, we've got an open top box. This is a classic pre-calc problem. It also plays a very large role in calculus later on, so I thought it'd be a good idea for us to take a peek at it. We know that the volume of a rectangular prism is length times width times height. In this problem, we have to identify what those 3 things are. The height, I would talk about as coming up from the box, so that's just x. My width, I'm going to call this front face, which ends up being this same piece here. I know the total distance is 20, so 20 is going to be involved, but I have to take away these 2 x's on either side. So that becomes 20 minus 2x. My length, which is going to be this distance down here, corresponds to that across piece. Instead of starting with 20, we start with 40, but it has those same 2 x's taken away from it. So it's going to be minus 2x. And we want our volume to be 1500. So I'm actually just going to set that equal to 1500. And then what do they want to know? They want to show this can be done 2 different ways, find the exact dimension of the box in each case. To be able to solve this, to find an exact x value, we could just guess and check x's, but that could be a really long time. I think what we're better off doing is subtracting that 1500 over, to force it to equal 0. Then we want to solve this. To solve this, it's some pretty annoying algebra. Our best bet is to FOIL all 3 of these out and turn it into a regular polynomial. But then based off the possible rational roots that we saw before, we'd have to take factors of 1500 and then divide them by factors of what's going to be 4. And that's a long list of different possibilities. You could guess and check with a whole bunch, and then once you find one, you could then proceed forward. What I might do in a problem of this nature is throw this into y equals on my calculator, and then scroll up and down on the table till I found an x value that made y equal 0. As it just so happens, when x equals 5, y is going to be 0. So that way we get our first solution, and then we can synthetically take it away. We can't synthetically divide it in at this moment because it's got to be in a polynomial form. So you really have to expand these 3 things before you could make progress. Once we know x is 5, we could turn around and say my length is going to be 40 minus 10 or 30, and my width is going to be 20 minus 10 or 10. So 30, 10, and 5 are one of my dimensions. This is a very similar problem, except it's playing around with the idea of girth. This formula of the length plus the girth is 108 is actually the United States Postal Office formula for how large of a box they will ship. So my length, they're talking about this long distance here. My girth would be that if I actually wanted to tie string around the box, that path there. So it's kind of like the lateral perimeter, as it were. So my girth, being 108, is going to be my length plus this spot here, b plus b plus b plus b. So it's going to be 4b. That's one of my formulas. But I also know my volume is 2200. And that's length times width times height. My length and width here are both b, so that's b squared L. If I'm trying to solve this problem, I've got two unknowns. I don't know what b is and I don't know what L is. But I've got two equations to be able to figure it out, which means we can solve this problem. I can pick either equation to solve for. It looks like this is pretty easy to solve for L. So I'm going to say L is 108 minus 4b. And then I can replace the L in this problem with that. So now I have a problem with just b's. If I distribute the b squared in, I'm going to get negative 4b squared. And then I'm also going to get plus 108b squared. I'm sorry, that's b cubed. And then minus 2200. And now it's set equal to 0. So now that's a cubic, which means I can solve it. Again, I'd be looking for factors of 2200 divided by factors of 4 and test each one of those to see if they work. If I have access to a calculator, again, it's much nicer to be able to put this in y equals, hunt up and down the table for x values that make y equal 0. Alright, that wraps up the old one, and now let's take a look at this new 3.5 and 3.6 and see how far we can make that happen before we run out of our 15 minutes. So if you had to solve x squared plus 1, you can't really factor that, so really your only option is to subtract 1 from both sides, and then square root. And you get x equals the square root of negative 1. Preferably, you actually get plus or minus square root of negative 1. That's undefined. We don't have a solution for that, and that's an absolute dead end. Until a guy by the name of Tarantula comes along. He says that this needs to have a solution in order to make math complete. So instead of just saying this can't be done, let's actually define it. Let's take this square root of negative 1 and actually definitively call it I, to stand for this imaginary number that we're just going to make up. Once we define I, it actually opened the world to a whole lot of new applications of math that had otherwise been impossible because we didn't know how to define this. It extends out into science as well. For i's, you really want to be comfortable with a basic pattern. I is just I, no big deal. I squared, you're squaring square root of negative 1. The squared and the square root cancel each other out. And it just makes negative 1. I cubed, you could make that same argument times I, so it makes negative I. And I to the 4th, you take that negative 1 we found before and square that, and it actually makes positive 1. The cool part is it actually cycles right back through there over and over again. So I to the 5th is the same thing as I. And I to the 6th is negative 1. I to the 7th is negative I. I to the 8th is 1. And so on and so forth. It'll follow that pattern forever. So every 4 repeat the same cycle. Once you get comfortable with these complex numbers, you realize that every power of I just reduces to a regular I. Which means any conceivable problem you could come up with that has imaginary numbers in it will always boil down to a number plus or minus a number I. This number plus or minus a number I is referred to as a complex number. Complex numbers overshadow every number you've ever heard of, whether it's a positive, a negative, a decimal, or a fraction. They're all part of this complex scheme. 2 is a complex number because it's the number 2 plus 0i. So all numbers fall within this complex spectrum. So let's take a look at I to the 303. We could, conceptually, just keep counting 5, 6, 7, 8, 9, 10, and go on and follow that pattern forever. But it's probably easier to try and figure out where this falls in the pattern of 4s. So what I would do is divide 4 into this number. 4 is going to go into 37 times. 4 is going to go into 23 5 times. And then look at that remainder. That means that we could rewrite this as I to the 75 times 4 plus 3. Now that, because of our exponent laws, I to the 75 times 4 could split out, and we'll say times I to the 3rd. This all is just 1, because I to the 4th, whether it's 1th or 75 times, is all just 1. And I cubed we know is negative I. So really, once you do this division, this remainder is just a new exponent of I. So it's this whole big mess is the same thing as I cubed. More complicated arithmetic follows the same idea. I cubed times I squared. We're going to add exponents. And then I cubed times 3i is 3i to the 4th. I to the 5th we know is just I. I to the 4th we know is just 1. And typically we write it like this so that it looks like a complex number. Complex numbers follow all the regular rules of math. You can add them, subtract them, multiply, divide, just like a regular number. With subtraction, you want to be a little bit careful. Kids oftentimes remember to make the 15 negative, but they forget to change the sign of the back one. So what I'm going to prefer to do is make this plus, and then just change the sign of both of these. At this point, it's just regular rules of math of combining like terms. The 9 and the negative 15 are going to combine together to make negative 6. 22 plus 16 is going to be 38. I. And that's my answer. So a complex number minus complex number is still a complex number. In math, we often refer to that as closure. Multiplication is kind of the same story. We just FOIL it out like regular. 30 minus 6i plus 15i minus 3, and then I times I makes I squared. General rule is you don't want I to have any exponent, so when you see an I with a bigger exponent, you immediately think about how to reduce it. I squared we defined as negative 1. Negative 3 times negative 1 becomes positive 3. 30 plus 3 becomes 33. Negative 6 plus 15 is going to be plus 9i. And that's my answer. Division's a lot more complicated. Essentially, somewhere along the way, somebody decided you shouldn't have square roots in the denominator. And this doesn't look like it has that, but remember, I is the square root of negative 1. So we resolve this the same way we resolve 4 minus square root of 3. We use the conjugate. Conjugate's the same thing as the bottom, it just has the opposite sign in the middle. Technically, this is the complex conjugate, although I wouldn't worry about that word so much. Conjugate's the key one you want. Up top, they FOIL together to make 12i plus 3i squared. Down the bottom, 4 times 4 is 16, plus 4i minus 4i, the middles cancel out, minus I squared. So by design, all the i's are going to disappear. I squared is negative 1, 16 minus negative 1 is 17. Up top, I squared is negative 1 again, and we get negative 3 plus 12i. This might not look any prettier to you, but the big advantage is we no longer have that I in the denominator, so we're following the rules of math. There's no square roots in the bottom. Squared. Resist the temptation just to say this is 16 plus 9i squared. This squared cannot travel across a plus sign. So what you really want to imagine is that this is 4 plus 3i times 4 plus 3i. Once we write them out side by side, we can FOIL it together just like before. Let's not jump that step. 12i plus 12i plus 9i squared. I squared becomes negative 1 times 9 is negative 9 plus 16 is going to be 7 plus 24i. So you realize it plays out just like regular numbers. They just got a few extra steps. It's kind of a hybrid between basic arithmetic and some of the polynomial work we were doing before. Alright, so to wrap up with this one, we're going to try and find values for x and y to make this true. Now, if this is going to be true, whatever evaluates on the left has to equal what happens on the right. Or more notably, this whole first term has to match up against this first term. So it's kind of like a little mini problem. 2x plus y equals 1. This coefficient of I has to match up against this coefficient of I. So 3 minus 5x equals 7. And again, we're in a situation where we have two unknowns, x and y, and two equations. I would focus on this right equation because it doesn't have any y's in it, so it should be a little bit easier. I could subtract 3 from both sides, and then divide by negative 5. And I find an x value. Once I know an x value, I can substitute it into this left equation. And now I have an equation that I'm just solving for y. Fraction times 2 is just going to multiply up top. Add 8/5 to both sides. I'm going to think about 1 as 5/5. So 8/5 plus 5/5 is going to be 13/5. And that's my y. So they wanted to know what x was, and they wanted to know what y is, and now we know them both. Hope you liked it.